Good day, viewers all over the world. You are welcome to Theorem online class. Today we want to look at mean value theorem. Mean value theorem. So what does the theorem state? Mean value theorem states that suppose f is a function is such that the first one, f is continuous on a closed interval AB. On a closed interval AB. Then the second one, f is differentiable on an open interval AB. This is an open interval, this is a closed interval. Then there exists at least one point C, that belongs to open interval AB, such that f prime of C is equal to f of B minus f of A all over B minus A. That is mean value theorem. And of course, mean value theorem is an extension of Rolle's theorem. So I want to believe that we are familiar with Rolle's theorem. So mean value theorem says that suppose f is such that f is continuous on a closed interval AB and f is differentiable on an open interval AB, then there exists, this is the symbol for there exists, at least one point C that belongs to open interval AB, such that f prime, that is the first derivative of f of C, is equal to f of B minus f of A all over B minus A. That is mean value theorem. So how do we prove this theorem? This is the theorem. How do we prove this theorem? In order to prove this theorem, we make use of the following. In order to prove this theorem, we make use of the following. Proof. So how do we prove this theorem? Let's see the proof of this theorem. The proof of the theorem. Let's see the proof of the theorem. So we define, under the proof, we are going to define. We define an auxiliary. We define an auxiliary function. We are going to define an auxiliary function, call it h of x. We define an auxiliary function h of x such that h of x satisfy. H of x will satisfy all Rolle's conditions. So we are going to define an auxiliary function h of x such that h of x will satisfy all Rolle's conditions. Then we now say that let h of x be equal. We let h of x be equal to f of x minus f of A minus x minus A raised by k dot. Let's call that equation 1. That h of x is an auxiliary function. H of x is an auxiliary function. So where k in that equation 1, where k is given as f of B minus f of A all over B minus A. So k is defined as what we have on the board. So in order to prove Rolle's theorem, we are going to make this statement. We define an auxiliary function. In this case, we call the auxiliary function h of x such that this is such that h of x will satisfy all Rolle's theorem, all Rolle's condition. Okay. We now let that auxiliary function h of x, we define it as f of x minus f of A minus x minus A into bracket k, where k is equal to f of B minus f of A all over B minus A. Then this implies that h of x is equal to f of x minus f of A minus x minus A. Then we have f of B minus f of A, everything all over B minus A. That's what we have. That's what we are going to get. So that's what we are going to get. Okay? That's what we are going to get. That is what we are going to get. Then from there, that's what we are going to get. So from there, if you want to prove mean value theorem, we must follow it step by step, as we have it on the board. Then we now say here, Roman figure 1. What can we deduce from h of x? Here, we note that h of x is continuous. This h of x is continuous on the closed interval a comma b. This is the closed interval a comma b. Then Roman figure 2. H prime of x, that is the derivative of this function, of this auxiliary function, will be equal to f prime of x minus k. That is, when we differentiate h of x, of course, this is a function, prime of f, then this one it will be viewed as a constant. Then when we differentiate this x here, when we differentiate this, we are going to have k, which is the same thing as what we have there. That's what we are going to have. So h prime of x, this will exist on closed interval a comma b. We can call that equation 2. That exists on closed interval. We can call that equation 2. Okay? We note equation 1. So then Roman figure 3. If you now substitute x equal to a, we say h of a. What are we going to get? If you substitute x equal to a, then this will be equal to f of, instead of x here, we are going to have a minus f of a minus f of a. That's what we are going to get, minus a minus a into bracket f of b minus f of a all over b minus a. That's what we are going to get. That's what we get there. That's what we are going to get there. But if you look at this critically, a minus a is equal to 0. Then everything there will cancel out. Then f of a minus f of a will also be equal to 0. So h of a will be equal to 0. That's what you are going to get. Please look at it very well. If you look at it very well, where we have h of a, f of a minus f of a will cancel out. A minus a is equal to 0. 0 multiplied by everything 0. So 0 minus 0 is 0. We have been able to get that. Then when we substitute for h of b from that formula, this will be f of b minus f of a minus b minus a into bracket f of b minus f of a all over b minus a. If you look at it very well, b minus a will cancel b minus a here. And at the end of the day, this minus here will control everything here. So f of b minus f of b, the minus is plus. The minus f of a plus f of a, this one will also be equal to 0. Let's follow. I want us to follow the step. Okay? So h of b will also be equal to 0. H of b will equal to 0. Then we now say thus h of a is equal to h of b and is equal to 0. We have been able to show that h of a is equal to 0. We have been able to show that h of b is equal to 0. Then we say therefore h of a is equal to h of b and is equal to 0. Therefore, we cannot make this statement. Therefore, we can make this statement. Therefore, we say therefore h satisfies. We say h satisfies the hypothesis. H satisfies the hypothesis of Rolle's theorem. Rolle's theorem. So that's what we say. Since we have been able to show that h of b is equal to h of a as equal to 0, it simply means that h satisfies the hypothesis of Rolle's theorem. It follows from there. It follows that there exists C that belongs to open interval a comma b such that h prime of C is equal to 0. That is the assertion. It follows that there exists C that belongs to a comma b such that h prime of C is equal to 0. H prime of C is equal to 0. So if you check that out, we can actually check it out from h prime of e from equation 2. From equation 2, you realize that h prime of c will be, when x is equal to c, h prime of c will be equal to 0. That is, h prime of c will be equal to 0. Hence, from equation 2, from equation 2, we are given hence h prime of c, h prime of x is equal to f prime of x minus k. Then what is k? This same thing as f prime of x minus k, same thing as f of b minus f of a all over b minus a. That is what we are going to, that's what we will have. That is k. And that's what we are going to get. Then if you look at this very well, h prime of c equals 0, this will equal to 0. That's what we are saying. Then, if that is the case, h prime of x is what we have there. So h prime of c will now be f prime of c minus f of b minus f of a all over b minus a is equal to 0. If that is the case, then what can we say about what we have there? Then we can transfer this to the other side so that f prime of c is equal to f of b minus f of a all over b minus a. All over b minus a. And that is what we are asked to prove. This is what we are asked to prove. This is what we are asked to prove. We are asked to prove. We have to prove mean value theorem. And that is what we have done. So I want us to go through it. Let's go through the whole process. It's very simple and straightforward. So that's what we are asked to prove, and that's what we have done. That's what we are asked to prove, and that is what we have done. So it's very simple and straightforward. That is that about Rowe's theorem. So I want to give example now. I'm going to give us 2 examples. I'm going to give 2 examples on Rowe's theorem. We want to verify Rowe's theorem. So I want us to verify Rowe's theorem. So how do we verify Rowe's theorem? Let's say example. I'm going to write the example on the board. Example. Say example 1. So let's see this example. Say example 1. Let's see the example. Verify the validity. Verify the validity of mean. Verify the validity of mean value theorem. Verify the validity of mean value theorem. Verify the validity of mean value theorem for the following. For the following functions. For the following functions. So what are the functions? The first one, where we are given f of x is equal to x plus 1 over s. That's the function. Then we are given a to be equal to half and b to be equal to 2. Then the second function, we are given f of x to be equal to x squared plus 2x minus 1. Then here we are given a to be equal to 0 and b to be equal to 1. So these are the 2 functions that we want to verify the validity of mean value theorem. So what do we do here? We want to verify the validity of mean value theorem. This mean value theorem is important. So what do we do here? Solution. I'm going to start with the first one. The first one, where we are given f of x to be equal to x plus 1 over s. That is what we are given. F of x is equal to x plus 1 over s. Then we are given a to be equal to half and b to be equal to 2. Of course, you know the interval is a comma b. This is lower and this is the upper interval. So what do we do? want to verify mean value theorem on this function. So we are going to find f of a and f of b. So here, f of half, which is a is half, will be equal to substitute wherever you see x, you change to half. That will be half plus 1 divided by half, that will be 2. That is 2.5. F of half is 2.5. Please let's check it out. F of half is 2.5. Then f of 2, b is 2, will be equal to 2 plus 1 over 2. Will also be 2.5. So f of a is same thing as f of b. F of b is 2. So it's also equal to half. So we have gotten that. Then if I differentiate f of x, I'm going to get f prime of x. Differentiation of x is equal to 1. Then this is, f of x is same thing as x plus x raised power minus 1. If I write it, that's what I'm going to get. If I write it, that's what I'm going to get. So when I differentiate f of x here, if I differentiate this, I'm going to get this as 1. This will come down. This changes to plus, then minus 1. I'm going to get to x raised power minus 2. This same thing as 1 plus 1 all over x squared. This is f prime of x. Okay? No, here is plus. When this comes down, here we change minus. So here will be 1 minus half. So that is f prime of x. That is f prime of x. So we know we have gotten the value of f prime of x. And of course, we say f prime of c, because we want to validate mean value theorem, will be what? 1 all over c squared. That's what we are going to get. So we now say by mean value theorem, what happened? We have f prime of c to be equal to f of b minus f of a all over b minus a. That is mean value theorem. By mean value theorem, that actually holds. Then if that is the case, by mean value theorem, we have f prime of c to be equal to f of b minus f of a all over b minus a. Then if that is the case, so what can you say about that? Then what is f prime of c? F prime of c is given as 1 minus 1 all over c squared. That's f prime of c. Is same thing as f of b. So f of b, we have gotten the value of f of b to be 2.5. When you check, minus f of a is also 2.5. All over b is 2, b is 2, and a is half. That's what we're going to get. So 2.5 minus 2.5 is 0. Of course, once the numerator is 0, everything here will be 0. So we have 1 minus 1 over c squared to be equal to 0. Okay? That's what we are going to have. That's what we are going to have. So invariably, 1 is equal to 1 over c squared. So if you cross multiply, therefore c squared is equal to 1. Then c is equal to 1. If c squared is equal to 1, c is equal to 1. So we have got the value of c to be equal to 1. C is equal to 1. So we have got the value of c to be equal to 1. Then what can we say? We have got the value of c to be equal to 1. So what can we say about c? This one, does it belongs to a comma b? Because c belongs to a comma b in mean value theorem. In mean value theorem, c belongs to a comma b. So in this case, we've gotten the value of our c. We've gotten the value of c to be equal to 1. So 1 belongs to 1 belongs to half comma 2. Yes, because these are open interval. So 1 is in between half and 2. Then we now say this verifies the validity of the theorem. So the first example, we have been able to show the validity of the first example. So we go to the second example. So what do we have in the second example? In the second example, f of s is given as x squared plus 2x minus 1. So where a is equal to 0 and b is equal to 1. Okay, that's what we have in the second example. So what is f of 0? That is f of a. Wherever we have x here, it will be equal to minus 1. Okay, then f of 1, which is b, that will be 1 plus 2. That will be 2. That's what we are going to get. Okay, then what is derivative? F prime of x is given as what? When we differentiate this will be 2x plus 2. That's what we are going to get. So when we differentiate, that's what we are going to get. So if f prime of x is this, then f prime of c will now be equal to what? 2c plus 2. That will be 2c plus 2. That's what we are going to have. Then if that is what we are going to have, then we just say by mean value theorem. By mean value theorem, we have f prime of c to be equal to f of b minus f of a all over b minus a. That is mean value theorem. Okay, that is mean value theorem. So in this case now, what is f prime of c? F prime of c here is 2c. F prime of c is 2c plus 2 to be equal to f of b is 2 minus f of a is minus 1. Minus times minus, that's plus 1 all over b is 1 minus 0. So from there, what do we get? Let's look at it. From there, what do we get? We have that 2c plus 2 will not be equal to 3 all over 1. When you cross multiply, we have 2c plus 2 to be equal to 3. So 2c is equal to 3 minus 2. So 2c is equal to 1. Then, when we look at it very well, we realize that c is equal to half. We are going to the value of c to be equal to half. Then this half, which is c, does it belong to on the interval between 0 and 1? Yes. Half is in between 0 and 1. Half is in between 0 and 1. Then we say hence the required result. So we have been able to validate mean value theorem on the two examples that we are given. So I want us to actually go through from the beginning. Let's look at the statement, because if you have to state and prove mean value theorem, then we start from the beginning. State mean value theorem, you have to state it, then you can prove it. Then, if you have to validate mean value theorem on a particular functions, just show that f prime of c is equal to f of b minus f of a all over b minus a. So I just want to do a kind of recap before we call it a day. How do we state mean value theorem? Mean value theorem states that suppose f is such that Roman figure 1, f is continuous on a closed interval ab and f is differentiable on an open interval ab. Then there exists at least one point c that belongs to open interval ab, such that f prime of c is equal to f of b minus f of a all over b minus a. That is the theorem. Then if you follow the teaching religiously, you are going to see how this theorem is being proved. So let's go through the proving. Then from the proving, I gave example. We have to verify the validity of mean value theorem on two different functions, 1 and 2, which we have been able to do. So I want us to go through the whole process. And if there's any question, you just write at the comment section. I'm going to attempt to those questions. So thank you.